Hi guys, so we're going to start year 13 today. We decided to start with chapter 26 because much of it lends itself better to us not being at school currently than some of the other chapters. There are a couple of bits in it that might need to explain in more detail when we come back, but most of it should be fine, and I'll point out these questions that are slightly harder to you and you might not need to answer them at the minute and then can come back to them later through the course. So yeah, it's chapter 26, it's radioactivity, and the first part is 26.1, the discovery of the nucleus. So here is some of the people that were involved in discovering the nucleus. Obviously you can just press pause and have a read through them yourself. This lesson is mostly about Rutherford, who basically discovered that there was a nucleus and what its charge was. Interestingly, here we've also got Bohr and Schrödinger, who are working at similar times, and they are really, especially Schrödinger, the start of quantum physics, really, and the particles topic we did at the start of AS. Learning objectives, you need to know how big a nucleus is, roughly, okay? And you need to be able to describe how the nucleus was discovered, which you do at GCSE, so it's a bit of a recap and then maybe using some more in-depth key terms, and then explain why the nucleus wasn't discovered earlier. So Rutherford, you probably remember this experiment from GCSE. I'll just go through some key points. So in 1897, J.J. Thomson said that every atom contains one or more negatively charged electrons. The distribution of that wasn't known, so that at that time there was the plum pudding model, which is a bit like a cookie where you've got the chocolate chips inside, which he thought were negative, and then you had this like the dough of the cookie that he thought was like positive. But he didn't know about cookies, so he knew about plum pudding, so he called it the plum pudding model. In 1911, Ernest Rutherford then proposed there was a positive nucleus with a cloud of negative electrons around it, which is what we're going to look at today. And then in 1913, that was confirmed experimentally using alpha radiation. And then this is how Rutherford confirmed that. This is a really simple diagram of what his experiment was. So here you've got just a surround, and inside is a vacuum. It's really important as a vacuum because inside here we're going to have an alpha source. Now alpha radiation is absorbed really, really easily by air. So if there was any air in this, then the alpha particles would hit it and then be stopped, and then they wouldn't reach this target here, which we'll talk about in a second. So you've got an evacuated chamber, and then inside here you've got an alpha source, which is surrounded on all other sides to stop the source escaping round here, to give you some false readings, and you just then have a very narrow beam coming through this gap here. What you then have in the centre, what he used was gold foil. Now he used gold foil because it's very malleable and it can be hammered extremely thin. Extremely thin. It had to be as thin as thing can be, so that you didn't have many atoms in a row. Okay, and then after that you have a microscope or some other device which can pick up what goes on this screen. So this is a zinc sulfide screen, and every time an alpha particle hits it, it lights up, and then the microscope was able to detect that. So he would then move this microscope around so it could move around the surround, and he basically counted how many alpha particles were hitting the screen at each angle. It's really important you have a thin beam here so that the angle you measure is very accurate. If you had a very, very thick beam, it would make this angle measurement here inaccurate. What did he expect to see? Well, he expected, because of the plum pudding model, some of the alpha particles to be scattered. So as the positive alpha particles hit the cookie bit of the cookie rather than the chocolate chip bits, the positive bit, he would expected some of those alphas to be scattered by that. What he observed was some of the alphas bouncing backwards. He said, "It's as incredible as if you fired a 15-inch naval shell at tissue paper and it came back." So they didn't really expect this backwards bouncing to happen, and he needed to explain it. So this is his experimental procedure. We've just discussed it a little bit. He has his narrow beam of alpha particles which all have the same kinetic energy. It's important that they have the same kinetic energy, as if they're moving through this and there's charges inside it, the ones that move slower would be acting on those charges for longer, and so they'd be deflected at an angle more. So they all have to be at the same kinetic energy, so that they're all moving the same speed, so that their speed doesn't affect their deflection, so it has to be controlled. They're fired at thin gold foil, and the alpha particles are scattered by the foil, and then they're detected at a distance r, so that would be the radius of this, from the foil. The microscope is then used to detect pinpoints of light emitted when alpha particles hit a fluorescent screen. The word fluorescent means that when something hits it, it lights up. He measured the number of alpha particles per minute at each angle of deflection. So he moved this a tiny amount, measured the number of alpha particles per minute, and then again, and then again, and then again. And he would have repeated that several times. So then he made those, he did that experiment, and then he made these observations. So if you have a look at the GIF, you can see it quite clearly. The alpha particles are coming through here, through a narrow beam, hitting the gold foil, and then you can see where the pinpricks of light go here, and occasionally there's one behind. So his observations: most of the alpha particles pass straight through the foil with little or no deflection. So only 1 in 200,000 actually didn't go straight through. Not 200,000, sorry, 2,000. So that's it. 1,999 went straight through. Small percentage of the alpha particles, about 1 in 10,000, was deflected through more than 90 degrees, so went behind this bit, so anywhere here. Only 1 in 10,000. So what did he deduce from that? What was his conclusions? Here again you can see the GIF of the particles going through. Most go straight through, some of them deflected at an angle, 1 in 10,000 deflected backwards. He said most of the mass of atoms is concentrated in a very small region called the nucleus at the centre of the atom. The nucleus must be positively charged because it repels the alpha particles, which are also positive, that approach it too closely. And then this is the diagram of what the particles would do depending on how close they are. So this one's the furthest away. It's positive, it has a charge of 2+. So that means that it has 2 protons, okay, which protons have the same charge of electrons, but they're positive. This one's the furthest away from the gold nucleus, not deflected at all. As you start to get closer, there is deflection, and that deflection gets greater and greater the closer you get. Oh, sorry, hang on. Sorry about that. Yeah, so the closer you get, the greater the deflection, until you get so close that as a particle comes in, it stops and then gets pushed away. In the case of this one, where it's straight on, it comes close, it won't actually touch the gold nucleus because of electrostatic repulsion. They're both positive, so they'll repel each other, and then is fired away. Now this distance d, just where the alpha particle stops, that distance between them is called the closest approach. It's the closest that the alpha particle can get to the gold nucleus. Obviously the gold nucleus has a charge of much greater than the alpha particle. It's got 79 protons, so it has a charge of plus 79 times the charge of an electron, which is 1.6 times 10 to the minus 19. could then sort of use this to determine the size of a nucleus. And there's two ways. There's one using probability, and then there's a much more accurate way. So if you're estimating the size of the nucleus with probability, I said to you that 1 in 10,000 alpha particles were deflected more than 90 degrees. So the foil must be very, very thin, otherwise the alpha particles will be scattered more than once. What we're trying to look for, ideally, would be one row of atoms, okay? And then you would know that every alpha particle would be scattered just once. However, that you can't do that. So there will be more than one row of atoms. So you might get one that goes straight through the first one, straight through the second one, then hits the third one, okay? So if you have a foil with n layers, so little n layers, the probability the alpha particle is deflected by a given atom, so one of those atoms, okay, would be 1 in 10,000 times n. Okay. So we know that the probability of it hitting an atom and being deflected is 1 in 10,000 because Rutherford carried out his experiment and this was the number that were deflected. So we know the probability of it hitting a atom and being deflected is 1 in 10,000. And we need to multiply that by n, which is how many atoms or layers of atoms are in the way, okay? So this probability depends on the cross-sectional area of the nucleus compared to that of the atom. So if the atom has a very, very tiny nucleus, then this number is very big, which is 10,000. If the nucleus was much bigger, then this probability would be much greater as well. So this number here would be smaller because it would be easier for it to be deflected by a particular nucleus. So what this sort of section is showing is this is the cross-sectional area of a nucleus, okay? So cross-sectional area is pi r squared or quarter pi d squared. That is the cross-sectional area of the nucleus, little d for nucleus. That is then divided by the cross-sectional area of the whole atom. So what you're getting here is a ratio of the area of the nucleus compared to the atom. Big D atom, diameter of the atom, little d diameter of the nucleus. The quarter pi's cancel, so you can see that then d squared, the diameter of the nucleus squared, will be proportional to the diameter of the atom squared. This proportionality can be got rid of if you insert a constant, and the constant would therefore be that probability, 1 in 10,000 times n, the number of layers you've got. So if you had 1 in 1 atom layer thick, then the probability an alpha particle would be deflected by that would be 1 in 10,000. If you had 2 layers, then the probability it would hit a particular atom would be 1 in 10,000 times 2, which is 1 in 20,000, because you have twice the number of nuclei. So the probability of it being hitting one particular one, okay, would be twice as small. An analogy for that would be, let's say that there is a wedding, okay, and the bride has one bouquet and she has 10,000 guests, okay, all lined up in a row. The probability, she then throws the bouquet. The probability that one of those people catches it will be 1 in 10,000. If you then add another layer of 10,000 people in a row, and then the bride throws the bouquet again, you now have twice as many people. So you're going to be twice as, you have to be, you're going to be twice as lucky to catch the flowers, if you like. There are twice as many people, so you're twice as unlikely to catch it. The probability, if you have 2 layers of people, would be 1 in 20,000. And then if you had another layer of 10,000 people, you'd be 1 in 30,000 as lucky to catch it. I hope that makes sense. So anyway, we get this equation which we can use to solve so if you say you knew the diameter of the nucleus,